Okay, so for the entropy of an ideal gas, we start off with equation 2.40, which is the multiplicity of an ideal gas of n particles. Remember that it's got those annoying factorials in there. We've already taken a bit of approximation getting it to this point. Okay, now we want to get rid of the factorial and honestly simplify it. Now, since we're interested in the entropy, we're going to be taking the natural log. Let's see here. So we're calling the formula for entropy. And we just put that formula there into omega here. Take k log omega. I'm not actually going to go through all the steps. Honestly, the book doesn't either. But the thing is, we're going to be able to get rid of the factorial by using Stirling's approximation. Which is equation 216. Okay, so applying that internally there, we're also going to be able to throw away some of the large numbers. Remember, we've got small numbers, large numbers, and very large numbers. The large numbers are those that are normally written as exponentials, 10 to the 20th power, or whatever. Whereas the very large numbers are going to be 10 to raise to a large number, like 10 to the 10 to the 20th power. So those large numbers in a few cases will be ignorable compared to the very large numbers. And we're going to wind up with there. This, I was going to say it's a fairly ugly looking formula, but it's a far sight better than the one for multiplicity up here, which has these factorials running around it. This is the Sacker-Tetrov equation. And it's the formula for the entropy of an ideal gas. All right, so see what we've got in it. The entropy of an ideal gas depends on the number of particles, appears in 3 different places here. By the way, notice both in the numerator outside the brackets, braces, and in the denominator inside, the logarithm inside there. So 2 different places. It depends on the volume here, and it depends on the energy of the gas here. So, make sure I've got room here. If you increase, see here, if you increase energy, volume, or number, any one of those 3, you will increase the entropy. Not that it is merely directly proportional to them, because it's in a fairly complicated formula here, but if any one of these 3 increases, the entropy increases. Notice also, when we're dealing with the system's energy, that the energy is proportional to the temperature. Or rather, I should say, the energy per particle. Let's see. Anyway, so often we'll have situations where the temperature is fixed, so we know that or if the energy is fixed, then we'll know the temperature is fixed, and so on. If we have a closed system where we're not changing particles. Okay. Let's see what happens if we vary the volume, holding the energy and the number of particles constant. All right, so we start off at an initial volume VI and end up with a final volume VF. So what is our change in entropy if we increase the volume, holding the others constant? So delta S is S final minus S initial. So we're just going to write down the Sacker-Tetrode equation for the final and the initial states. And by the way, the book does not put braces on the outermost one, and they don't put brackets on the next inner one. The book uses brackets on the outermost and 2 sets of parentheses inner. And I just want to make it a little easier to follow because you've got a lot of nested terms in there. So let's see, this will be V final over N. Oh, that's squared there. And notice, by the way, that you've got this 5 halves, plus 5 halves, stuck outside the natural log. So you have nk times, in braces, the natural log of all this stuff, and then plus 5 halves. Which is going to be nice, because that 5 halves is a constant, so this will often drop out in some cases. Now we've got the initial over N. Okay. The only thing different here are the V initial and the V final, and of course the sign between them. Let me show you we're going to break this up. All this is at this point is algebra and knowing how to handle a logarithm. But I want to show the steps because it looks a little intimidating. So, these are the two things that change between them. Now, we've got nk times. First term is this log, which goes up here. And the second term is that 5/2. So let's distribute the nk in both sides here, in both terms here. I'm going to just put a squiggly line for whatever's in the parentheses here, rather than bothering to write all of that out, because it's the same in every case. All right, so I've got nk times the natural log plus nk times 5/2. Over here, I've got minus nk times the natural log of the initial over n times the stuff in parentheses to the 3/2 power. And then again the minus nk times 5/2. So we've got plus nk times 5/2, minus nk times 5/2, those cancel. The next thing is that I've got nk natural log of df over n times that stuff in parentheses. Let's see, by the way, I could just put it this way and do it all in one fell swoop. Something times a natural log minus something times a different natural log. If I have a difference of two natural logs, how can I combine those? Natural log of A minus natural log of B is the natural log of?
A minus B.
A over B, right. So we've got nk times the natural log of this here divided by that there. There we go. Everything is the same in the numerator and the denominator except for VF and VI. And of course I run out of room just when I'm at the bottom. I hate having to move it all over, but I'm going to. So delta S equals nk times V final over V initial. When U and N, the energy and the number of particles, are constant. So what kinds of situations do we have where the energy and number of particles are held constant while the volume varies? Well, for example, a quasi-static, meaning very slowly done, quasi-static isothermal expansion or compression. Expansion and compression involve changes of volume. Isothermal means the temperature stays the same, and we're dealing with a closed system, so we have a constant number of particles. So with that, and the temperature staying the same, the energy is constant as well. So for example, quasi-static, isothermal. The book just talks about expansion, but it applies for compression as well. There. If you recall really, really well, not that I'm expecting it, but you might remember equation 1.31. Yeah, 131, which deals with a quasi-static isothermal expansion or compression. And in that case, we found that the heat flow, this is back in chapter 1, the heat flow for an isothermal process like that, on a PV diagram, remember, the isothermal processes look like this, a nice hyperbola. And if we go from V initial to V final, like that there, or the other way around, the heat flow during that is Q equals NK times the natural log, NKT times the natural log of V final over V initial. Boy, doesn't that look a whole lot like what we found with the change in entropy right here. The only thing missing was the temperature. So what we see is that if we're making an expansion, an quasi-static, so it's done slowly and smoothly, quasi-static isothermal expansion. Doing like this. Final volume is greater than the initial volume, so you get the natural log of a number greater than 1. Natural log of a number greater than 1 is greater than 0, so there's a positive heat flow. So if it's an expansion, Q is greater than 0 then. We're adding heat to the system as it expands, and by this here we see that we're also raising the entropy. Let me circle that this is an expansion for those two cases there. Heat flows into the system, and entropy is raised in the system. In fact, one nice little consequence of this is that you'll be able to see that in this case, the change in entropy is simply Q over T. For this case. We'll find more general cases later on, but that's mentioned in one of the homework problems. Okay, so adding heat raises the entropy of the system. Entropy flows into the system with the heat that it takes in. But that's not all. We have other cases where that doesn't happen, or where we raise the entropy without adding any heat. I know this thing is able to zoom in, but it won't. Well, everybody can squint today. Okay, now we're going to talk about, for the entropy of an ideal gas, with what's called free expansion. The previous example I used was a quasi-static expansion. You have a cylinder where the gas is contained, and you've got a sliding piston, and you gradually move that piston out, and the gas expands to fill the volume left behind. Fair enough? Now, what happens? By the way, don't you like the dramatic pauses I make in the middle of sentences when I'm about to draw something? Completely unintentional, I just forget to draw it until I've already started saying. What happens if we have the same cylinder, sides A and B, and rather than letting that partition gradually slide on over like that, allowing the gas on side A to fill the entire volume, what if I just, and this is a vacuum here, what if I just punch a hole in it? Little foil layer there, and I punch it. That's not a quasi-static process. The conditions are not almost the same from one moment to the next. You've got a very sudden kind of a change there. In this case, then, the particles rush in rather quickly. An interesting consequence of doing it this way is that the work done in a free expansion, as this is called, is zero. Now, why? Because the particles in the act of expanding into the other side of the chamber, in filling the whole volume, the particles do not push against anything in doing so. They just move into a free space. It is not quasi-static. It is not, as we will talk later, a reversible process. Think about this. If you had a piston there that expands, of course you've got this pressure of the gas pushing against the piston, wanting to make the piston move. So let's say that we've got this situation here with a sliding piston, and the piston is pinned in place so that it can't move. Vacuum is on side B. Now we release the pin, allow the piston to move freely. What's the gas going to make the piston do?
Move forward.
Sure, right. So the gas does work in expanding, as we've calculated in chapter 1. We could, in principle, not that we have to, but we could hook that piston up to, let's say that we have in moving, we have the piston tied to a chain and a weight and a pulley system, so that in expanding, the gas expanding, the piston moving this way pulls a weight up off the floor. So the system does work on the piston, which then pulls the weight up on the floor. We could later on recompress the gas by pulling that weight back down. I think I'm not setting it up quite right. But anyway, we could recover the work done, that's energy. It's been transformed from this expansion into gravitational potential energy of this weight moving off the floor. We could push that weight back down, lower the weight's potential energy, and turn that potential energy back into energy in the system. All right? What has been done can be undone in that case. You can't do that here. No work has been done. There is nothing we can do in this setup to squeeze those particles back in. We have no piston that they pushed out against. I haven't quite said it correctly, but hopefully you get the gist of it. So the work is actually zero. They have not moved the surface out that way. Next thing, how much heat has flowed into the whole system here during this free expansion? Well, we can isolate it, insulate it from the rest of the universe, so there's been no heat flow across. We've had an expansion which accomplished no work and had no heat flow. Remember, the isothermal expansion, it's isothermal, constant temperature, because we have allowed heat to flow into the system during the expansion, which keeps the temperature constant if we do it right. In this case, no. We've enabled an expansion with no heat flow and with no work. Therefore, first law of thermodynamics, delta U equals Q plus W, the change in the system's internal energy is 0 plus 0, which all adds up to 0. So for a free expansion, there is no change in the system's internal energy. It just takes up twice the volume. Let's say we started that partition off halfway down the middle, right down the middle. It takes up twice the volume, but it has not changed its internal energy. So in this case, before I talked about with a quasi-static isothermal expansion, entropy flowed into the system with the heat that moved into it. Entropy moved with the heat. In this case, there's no heat flow and no work. So what about the entropy? Well, if we take a look at back at equation 2.51, where I derived the, using the Sackler-Tetrode equation, and looking at the change in entropy of an ideal gas when you hold U and N constant, number of particles and the system's internal energy, and only allow change in volume, well, U has been held constant, delta U is 0. So that's satisfied, and we're not allowing any particles to escape the system or come in, so that's satisfied. So that equation I derived right over there is delta S equals NK times the natural log of V final over V initial. So recall that from just a minute before. Let's see here. U and N constant, and that both of those are satisfied. In this case, we have had an expansion, so V final is greater than V initial. That's greater than 1. Therefore, the natural log of that ratio is greater than 0. And that means delta S is greater than 0. So the entropy has increased despite the fact we've had no flow of heat into the system. Whereas with a quasi-static isothermal expansion, like a slow expansion of a gas in the cylinder as heat flows in, we had the entropy increased from the flow of heat into the system. That heat brought entropy along with it. But here, we've created new entropy, I was about to say out of thin air, but that might be somewhat misleading. We've just created new entropy without any flow of heat. So, the change of volume itself can do that even without any heat flow. Okay, and we'll talk more about tree expansion later on when we get to reversible and irreversible processes. Okay, entropy of mixing next. Let's say we have a container with two different gases in it. We have gas A on this side and gas B on this side. Now, I don't have any color chalk, so I can't color the particles differently, but let me use circles and crosses here. There we go. Now let's assume for the moment that we, for simplicity's sake, we have the same energy for each one, the same volume for each one, and the same number of particles. I can write this closer together. Okay, UA equals UB, VA equals VB, NA equals NB. Now we remove the partition. And we allow the gases to mix. We're still keeping track of which particle belongs to which gas, but they can move into each other's spaces. Okay, so they gradually move on across like that until they've mixed. What happens in mixing is that the entropy increases in this case as well. The way that we can find this out, and by how much, is to treat each gas as a separate system, even after they've mixed. What this means is, when you look for the change in A's entropy, you ignore the fact that B even exists at all. As far as A is concerned, there are no particles of B there. And the reason we can do this is that one of the premises of having an ideal gas is that the space between the molecules is much greater than the size of the molecules themselves. So they never crowd each other out. If they ever did get to be where the space of the individual molecules taken up by gas B becomes where the particles themselves are taking up some significant fraction of space so that A was not able to move in there, we wouldn't have an ideal gas. And we have a different way we have to treat that, and that's all the later chapters. If it's an ideal gas, and the gases around us in the air and so on are pretty close to that, the individual particles themselves occupy a tiny, tiny fraction of the total space. So what I mean by this is that, let's say if we've got oxygen and nitrogen in the air, two major components. The fact that there's oxygen in the air doesn't matter to the nitrogen as far as where it can move. There's plenty of empty space out there for it. Okay, so we treat each gas as a separate system when in this process. So for A, change in its entropy is, well, let's see here, we've got the equation from before. So we use the change in entropy for that we use for free expansion. If we suddenly get rid of this barrier, each of these gases does a free expansion into the other part of the space. Remember, ignore the existence of the other gas. So we pull up the barrier, A makes a free expansion into the entire volume, B makes a free expansion into the entire volume. Now, the equation for the change in entropy when the number and energy are held constant and only volume changes is simply NK natural log of V final over V initial. So I've got V sub final A over V initial A. Okay. If we had the barrier right down the middle, so that A and B each had the same volume to begin with, the total volume, the final volume, is twice the initial volume. So V final over V initial is 2. For B, the same thing. V final for B is twice V initial for B. So that's 2. So what is the total change in entropy for the combined system? Here I need to move the camera around just a bit again. The change in the total entropy is the change in entropy of A plus the change in the entropy of B. This might not be immediately obvious. But let me show you something, because this sort of a thing here, if the entropy, total entropy is SA plus SB, then the change in the total entropy is delta SA plus delta SB. Let me just prove this on the side here. And I have to move the camera even more. Delta S total is S final minus S initial. S total is SA plus SB. So S final is SA final plus SB final minus S initial. So it's minus SA initial plus SB initial. I distribute the negative sign. Now I pair up the SAs and I pair up the SBs. So here I've got SA final minus SA initial plus SB final minus SB initial. And that's delta SA plus delta SB. So for any function which is merely the sum of other functions, the change in that function is the sum of the change in the other functions it's made of. The other additive terms. All right. Using that there, let's see here. Change in entropy of A and the change in entropy of B are the same. So the change in the total entropy is just that. Okay, so that is the entropy of mixing. By the way, this natural log of 2 only comes about because the ratio of the volumes was a factor of 2. It could have been some other factor coming here. Okay, but there's a little quirk to this. I had 2 different kinds of gases here, distinguishable particles. What if they were the same kind of gas? Would the entropy increase noticeably if I had the same gas on side A and side B, and then I remove the partition? I mean, you'd think from the formula that it would, because, well, particles over here, move the camera back. The particles over here do a free expansion over that side, the particles here do a free expansion over this side. What's the difference? But then you start thinking about it and you realize, well, if I've got an identical gas with the same number, volume, and energy on both sides, I've got a barrier down here. If I just remove the barrier, nothing's changed. Or hardly anything. There's actually some very small changes. Each individual particle has more volume it can go over, but the whole gas really hasn't had any appreciable change. So this entropy of mixing only applies when you have distinguishable particles. If they are indistinguishable particles, you don't have it. And let's see here. The reason, let's see here. If you start with the same gas on both sides, this is page 80, then the entropy doesn't increase at all when you remove the partition. He says technically there is a slight increase because the distribution of the molecules between the two sides can now fluctuate. One particle can go to the other side. But the multiplicity only increases by a large factor, and these other factors are very large factors, so that it's washed out. So, another way of thinking about it, to make to compare the distinguishable versus indistinguishable particles. If you forget the partition, if we start off with just a mole of helium in the chamber, you've got the total entropy given by the Sackur-Tetrode equation, and I need to write that back up here. In fact, we're going to write up the multiplicity of an ideal gas and the entropy, the Sackur-Tetrode equation. Okay, that's the multiplicity of an ideal gas of n particles. And the entropy, which is just K times the natural log of this, is the Sackur-Tetrode equation. Okay. Now, let's see here. That 1 over n factorial in the multiplicity, that's the key thing. Because if you look back on page 71, when we had, once we started adding more than one particle to our ideal gas, we derived the multiplicity for an ideal gas of one particle, but once we started dealing with an ideal gas of two particles, we realized that say you've got molecule 1 up here and moving that way, and molecule 2 is over here and moving that way. If these are indistinguishable molecules, they've got the same mass, all the same properties, then switching the identities of which molecule to switch does not change the state of the system. So these represent identical states. It's the equal sign there, if they are indistinguishable. So that's a condition there. If they're indistinguishable, those are the same. So in counting up the multiplicity for a gas of n particles, we have to divide, if they're indistinguishable, we have to divide by the number of particles factorial, which represents dividing out all of those identical states here that represent switching the identities of the molecules. It's only if they're indistinguishable that 1 over n factorial creates this factor of 1 over n under the V. Volume per particle there. That 1 over n comes from the 1 over n factorial. Okay. So if we have indistinguishable molecules, we've got these terms here. And that leads us to the conclusion that we had before. If we had distinguishable molecules, conclusion we had before, that's not true. If we had distinguishable molecules, we would not have that term there, and we would not have this, the 1 over n here, if they were distinguishable. And make sure that there are no other effects. For distinguishable molecules, we'd have a plus 3 halves out here as well. Take a look, that's in the book there. Okay. And let's see. If we were dealing with these distinguishable molecules, if all the molecules in the gas were distinguishable, if that applied to regular ideal gases, you'd wind up having these weird consequences. You'd be able to decrease the entropy of the gas by just inserting partitions very easily down into the chamber. All of a sudden, the entropy gets lowered, and it violates the second law of thermodynamics. You could lower the entropy without doing work on the system. And that's not the case. So that factor there comes in as quite important. One thing about lowering entropy, which is was raised fairly early on, back in the 1800s. James Clerk Maxwell had recognized a problem, or at least he put out a thought problem, that could we lower the entropy without doing work on the system, and without changing the macroscopic state otherwise? And he said, well, let's imagine for a moment, if we've got this quasi-static isothermal expansion, heat flows into the system carrying entropy in with it. The entropy is raised as the heat goes up, as the heat comes in. What if we could separate high-speed and low-speed molecules within a chamber here? So temperature, remember, is your average kinetic energy per molecule, or average energy per molecule. They're bouncing around. What if we could separate the high-speed ones from the slow ones? So we've got a gas here with all different speeds of molecules. And what if we just put a partition down here with a little swinging door in it? And every time a high-speed molecule comes by, we open the door and let it on through. Every time a low-speed molecule comes by, we close the door and it bounces off and stays over here. Same thing over here. If a low-speed one comes through from this side, we open the door and let it through. So that over time, just by opening or closing the door, we separate all the low-speed ones on this side and all the high-speed ones on that side. Then the temperatures would be different. High-speed molecules over here, higher temperature, higher energy per molecule. Low-speed ones here, lower temperature. Now, looking at the equation for entropy, we would have lowered the entropy in doing this. We would have undone that entropy of mixing. We would have unmixed the gases without doing any work on them. This would seem to violate the second law of thermodynamics. This was the idea of a little, some little intelligence sitting here next to the door, opening and closing it, was nicknamed Maxwell's demon. And became the subject of a whole lot of thought problems in trying to work out, could this actually be done in any way whatsoever? And there are a lot of very clever responses to this. And I don't mean that in a sarcastic way. I mean very clever ways of thinking through the consequences, some of which were even done by Richard Feynman, mid to late 20th century. And it was shown that in any way you try to separate these by speed, you'll always wind up increasing the entropy regardless. For example, one thing is, in order to decide whether to open or close the door, you have to process information. This gets into something called information theory, which is very closely tied into thermodynamics. And in having to think through it, you actually would have to generate some waste heat in the process of processing the information. And that waste heat would more than make up for the entropy that you thought you were reducing the system by. You'd wind up creating more in the process there. There are a lot of other things as well, but anyway, it always comes down to that. The entropy will always increase if you're not doing work on the system there. Furthermore, you can decrease the entropy of a system. That's okay. You can lower the entropy of a system, but in the process you must increase the entropy of the rest of the universe by more than you lower the system by. Think again, this is a rather crude example, but think again of how I've joked that the second law of thermodynamics, that entropy will always increase. Sorry, there are many ways of putting it. The entropy of an isolated system will never decrease. And it will, in fact, increase whenever possible. An isolated system is one you're not doing anything to. It's completely isolated from the rest of the universe. Now, if it's not isolated, you can lower the entropy of it. Fine. But in the process, that entropy is going to go somewhere, in a sense. It can't be, the total entropy of the universe can't be reduced. It can only be increased, and it can be increased. I've sometimes joked that the second law of thermodynamics is equivalent to your mother saying your room's not going to clean up itself. So there are a small number of ways to have a neatly arranged room. There are a large number of ways of having a messy room. Okay, so there's sort of our multiplicity of it. Your room over time can collect dust, things like this by natural processes. You've got your books neatly stacked up and alphabetized or whatever. But let's say you've got, jokingly, earthquakes or whatever else like that. The system can be jostled around a bit and things can fall out of order. Or you can just go in there and you mess things up. It's easy to mess things up, it's hard to straighten them up. If your room is isolated, you're not in there, you're not doing anything to it, the entropy is not going to decrease. It's not going to clean itself up. It can get worse, but it can't get any better. But when this is all right, your room's not going to clean up itself. Entropy is only going to increase on its own. So go in there, do work on the system, and lower the entropy. Straighten it up. That requires you to go in and do work in a figurative sense now, do work in straightening it up. You can lower the room's entropy. But in the process, what have you done? Well, you've gone in there. How did you have the energy to, using the word energy loosely, but how did you have the energy to straighten it up? Well, you had to eat food in order to have energy for your muscles to burn. So your muscles converted chemical energy into kinetic energy in moving things around. And what happened in the process? You also generated heat. You warmed up by eating the food. You maintained a constant internal body temperature. So you're radiating waste heat out into space as you do this. And if you calculate, which you could in principle, you can find that the entropy radiated out into the rest of the universe by the waste heat you generated by eating and going in and cleaning up your room more than made up for the entropy that you lowered in your room. The rest of the universe raised by much more than that. So, the entropy of any little part of the universe can be decreased by various interactions, but the entropy of the whole universe will go up in the process, or at best stay constant. And you're rarely ever going to get it really to stay constant. It just likes to go up all the time. Another thing then, reversible and irreversible processes. The book has a nice discussion on this at the very end of the chapter. Let's see. the processes that create new entropy are irreversible. You take a coffee cup, shove it off the ledge, it falls on the floor and breaks, its entropy is increased. There are a lot of ways for it to look broken, but only one way for it to be put together. While all the laws of physics individually are reversible, you're not actually going to see a broken coffee cup spontaneously leap off the floor and get back on the shelf and stick itself together. Every individual bounce and things like that could go the opposite way, but the collection of them won't go back to that way there. He says it's interesting to think why, a process that leaves the total entropy of the universe unchanged would be a reversible process. Individual collisions between subatomic particles, in principle, are reversible. But macroscopic processes that involve 10 to the 20th, 10 to the 23rd, particles are irreversible because you've got so many different ways the outcome could be. Let's see here. Heat flow is always irreversible. Heat flow is a statistical kind of a process. And an interesting example that he only mentions in passing is examples of large entropy increases and that are highly irreversible. Sunlight warming the earth. It's a neat example of the change in entropy there. Roger Penrose, the great cosmologist, has a nice little discussion of this in his book, The Road to Reality, subtitled A Complete Guide to the Laws of Nature. And he shows in a diagram, sunlight warming the earth involves an increase in entropy. And the reason why, so there's the sun. Apparently the sun is a little shaded because it's a sphere. It's a little kind of shadow on one side here. Here's the earth. Sunlight has a spectrum the number of photons as a function of wavelength. Let me write here intensity versus wavelength. Black body radiation. So you have a peak and then it tails on off. There's that characteristic shape of black body radiation. You're both familiar with that? Okay. Where the peak is tells you the temperature of the thing glowing. The higher the temperature, the more this peak shoves over to the blue end of the spectrum. The cooler it is, the more it shoves over to the red end of the spectrum. Okay, so the sun has a temperature of about 6,000 degrees Kelvin. It peaks right in the, there's some debate on this, some discussion of this, in the middle of the visible range of wavelengths. Okay. The peak is in the yellow, the greenish yellow part of the spectrum. There. Now, so what you have is a certain number of fairly high energy photons coming to hit the Earth here. Okay, so let's say you've got this, let's say it's a small number of high energy photons. The total amount of energy is pretty large, but it's concentrated in a moderately small number of photons. Now, the Earth absorbs that radiation. The temperature of the Earth stays pretty constant at about 300 degrees Kelvin. If the temperature stays constant while heat is flowing in, what else must be happening?
The heat's got to be going out.
Right. So it re-radiates that back out into space, but the spectrum of the Earth, which has a lower temperature of 300 Kelvin, the black body spectrum peaks in the infrared. So this is the visible part of the spectrum, short wavelength, high energy. This is in the infrared part of the spectrum, long wavelength, low energy. for a small number of high energy photons hitting the Earth, you have a large number of low energy photons radiating that energy away from the Earth. So what happened to the entropy? The entropy of a small number of high energy photons is much lower than the entropy of a large number of low energy photons. Sure, each one has less energy here, but you've got a lot more photons making up for it, so the total entropy radiated away is much higher. Entropy increases. And in fact, in his book, he relates this to the habitability of the universe as a whole. That in order to have a habitable universe, you've got these, well, it's part of it, but you have these increases in entropy. And you will always need to have these low entropy sources to allow life to exist. If the entropy, if you didn't have these stars, which are low entropy sources, entropy sinks? No, it's not quite right. Anyway, you wouldn't have a habitable universe. If it were the same temperature everywhere in space, life couldn't exist. You wouldn't be able to convert small numbers of high energy particles into large numbers of low energy photons. Okay, life thrives in this process here. That's where we're going to end it today. And that's the end of chapter 2.